Okay, so last class session we discussed how to calculate and predict the charge of an ion in an ionic compound. Now, there are two major methods. We can use the formula method, where we solve for the charge of our cation by taking the total charge minus the charge of our anion times the number of anions over the number of cations. This equation relies on the central principle that the total charge of an ionic compound is the sum of the total charge of each ion in that compound. Now, the one thing that's a little bit interesting is that this equation method can be applied to determine the charge of a cation in a charged complex. Does everyone see that our total charge is not 0? Does everyone see this -1 for the total charge of this iron hydroxide? So then, if we're solving for the charge of our iron atom in this iron hydroxide complex, we take the total charge, which is -1, this is our total charge, minus the charge of our anion, and in this case, our anion is hydroxide, so it has a -1 charge, and we have 4 hydroxide anions. So we multiply that by 4, and then we divide by the number of irons, which is 1. That in turn gives us a charge for iron of +3. Does everyone see how this example is slightly different from the earlier ones that we've done? This time we have to account for the total charge in our calculations. Does this make sense to everyone? Is everyone comfortable with this idea? So let's have everyone work on a follow-up example. I'd like you to tell me the charge of copper in the following complex, in the following copper chloride complex. So I'd want you to use the same equation and solve for the charge of copper. And let's take about 2 minutes to work on this example, and then we'll come together as a group to discuss. And remember to have the correct sign for the total charge, where our total charge is -2 in this case. And let's try to get a few more responses in the chat, and we'll discuss this example in another minute or a minute and a half. Does anyone have another proposal for the calculated charge of copper? So we see a nice pool of responses in the chat, so let's discuss. So our total charge is -2. What is the charge of chloride? What is the charge of chloride? What is the charge of chloride? -1. So we plug in -1. And how many chloride ions do we have? How many chloride ions do we have? 4. So that in turn, when we divide by the number of copper atoms, that gives us a charge of copper of +2. Key thing to keep in mind, make sure that you pay special attention to the sign in this calculation for both of the charges for the molecule and the charge of our ion. Does that make sense? Is everyone comfortable with this example? Perfect. So let's showcase an example where we have to use our charge rules and fill in the blank with at least 3 reasonable atomic ions, a transition metal, and a polyatomic ion. Okay, so looking at the following example, we can quickly figure out the charge of each of our components. So chromate has a charge of 2-, which matches our table. And this blank ion has a charge of +1. So what atomic ion would have a charge of +1? What atomic ion would have a charge of +1? Would someone like to help me out on this?
Group 1A,
Yes, and what would be a specific example of that?
like sodium.
Yep, exactly right. So sodium plus would be one potential fit for this chemical formula. Okay, what about a transition metal? What about a transition metal? Would anyone like to propose a transition metal?
Ag.
Yep, silver plus, that would work. You can also do copper plus, you can do cobalt plus. Essentially any transition metal would work unless it's a fixed charge with a charge other than +1. So there are a lot of reasonable answers for the transition metal. What about polyatomic ions? What polyatomic ion has a charge of +1? It's one of them on the list and it's pretty common. It's used a lot.
Hydroxide.
Hydroxide has a -1 charge, but you're on the right track. What about a +1 charge? If you look at the, what was that?
H plus. Oh.
Ammonium.
Yes, exactly right. NH4 plus. That's the most common polyatomic ion with a +1 charge. Does this example make sense to everyone? So this serves as a way of testing if you know how to determine the charge of an ion, and then if you know how to sort different atoms and polyatomic ions based on their preferred charge. Does that make sense? Any questions on this example? So let's look at the following, and I'd like you to fill in the blank with at least 3 atomic ions and 1 polyatomic ion for a formula of a compound containing cadmium, remembering that cadmium likes to adopt a 2+ charge. So let's spend about 3 to 4 minutes on this example, and I'd like you to list the atomic ions and a few polyatomic ions that would fit in this formula. And we'll discuss this example in about 3 minutes. And let's try to get some responses in the chat, and then we'll discuss in about another 2 to 3 minutes. And if you have a question, don't be shy to ask it in the chat or verbally, and I'd be happy to address your question. So we have someone proposing an atomic ion of O2 minus. Okay, wonderful. Let's try to get some more responses, and really don't be shy to chime in. Even if your responses are different from your classmates, they still add to the discussion and they may be right. So don't be shy to contribute to this overall class discussion, and we'll discuss in about another 2 minutes. We also have a proposal of sulfate, which is SO4 2 minus. And really don't be shy to provide your proposed atomic ion or polyatomic ion. There are many to choose from. And the mere act of attempting to explain your proposed solution can help you integrate this concept. So we have selenium 2 minus, tellurium 2 minus, and polonium, sure. So I don't see many polonium ions. Carbonate, yep, CO3 2 minus, that matches our trend. In the last remaining minute before we discuss this example, does anyone else have another proposed atomic ion or polyatomic ion? We'll give everyone about another 30 seconds to a minute. Okay, so let's discuss this example and let's really summarize our reasoning. So if we cross our charges, we'd get initially cadmium plus and blank minus. However, we know that cadmium is a fixed charge transition metal, adopts a 2+ charge. So we'll multiply both of our charges by 2. That gives us cadmium 2+ and blank 2 minus. And as you've seen, we filled in atomic ions with a charge of -1, which are group 6A atomic ions. And for our polyatomic ions, we look at our table and find polyatomic ions with a 2- charge. Does this make sense to everyone? Does this make sense to everyone? Any questions on this example?
Can you repeat everything? I don't get it.
So you're solving for, you're trying to figure out what ions you can place in the blank that would generate a neutral ionic compound. You have a 1-to-1 ratio of each of your 2 ions. So you cross the charges, and that gives us an initial predicted charge of cadmium plus and blank minus. Okay? The problem with that is cadmium, we know for a fact, adopts a 2+ charge. So in order to get the correct charge for cadmium, we'll multiply both of our charges for our cation and anion by 2. That gives us cadmium 2+, which matches our predictions, and blank 2-, which is our target, and which tells us that for our atomic ions and polyatomic ions, we need to fill in this blank with atomic ions and polyatomic ions that prefer a 2- charge. This will be our 6A elements for our atomic ions, because of course our charge is equal to our group number -8, and 6 - 8 is -2. And for our polyatomic ions, we'll look in our table and find the list of polyatomic ions with a 2- charge. Does that make sense? Does that?
Yes, thank you.
So, any other questions before we move on to the next major topic? Okay, so let's keep going now and let's talk about nomenclature. And nomenclature is the process for naming compounds. And before we do that, you need to learn how to classify your compounds. So binary compounds have exactly 2 different elements, but any number of atoms. So for example, SO3 would be a binary compound because we have 2 different elements. Likewise, water can be a binary compound. Other examples include sodium chloride and carbon monoxide. We have exactly 2 different elements with any number of atoms. Now, binary ionic compounds, they have exactly 2 different elements with a metal cation and a non-metal anion. So for example, sodium chloride, lithium sulfide. In sodium chloride, we have sodium plus. Let me write that more appropriately. So we have sodium plus, which is our metal cation, and Cl minus chloride, which is our non-metal anion. They don't need to be, the cation and anion do not need to be in a 1-to-1 ratio. The only criteria for a binary ionic compound is we have exactly 2 different elements. Binary covalent compounds, we have exactly 2 different elements covalently bonded, and binary covalent compounds are composed of 2 different non-metal elements like carbon monoxide, nitrogen dioxide, dihydrogen monoxide, or water. These are all covalent compounds because we have exactly 2 different non-metals. The criteria for binary covalent compounds is exactly 2 different non-metals. Okay, so really pay attention to whether you have metals or non-metals in your chemical formula. Does that make sense? Yes, so the exam will only cover content up to last week, but this content is important because you both need it to complete one of the reports due this week, and it will show up in prevalence on exam number 2, which is the next exam after this one. So, any questions on binary compounds, ionic versus covalent? Now you may say, why do I care about this? What's the purpose? Well, different classes of compounds have different rules for naming. And if you can't classify a compound, you're going to have trouble naming the compound accurately. Okay, so let's start off with the first group, which are binary ionic compounds. I like to call the first type of binary ionic compounds class A because they have a main group metal and a non-metal. And to name these compounds, it's really straightforward. You write the name of your metal cation just directly from the periodic table, and then you write the name of the non-metal anion, except, and this is the trick, you replace the ending with IDE. Now, each element name has a common stem, and you're going to need to memorize these common stems. This is important to be able to fully name binary ionic compounds. Now, there are a few unique stems that often catch students off guard. Oxygen converts to oxide when you're describing the anion. Phosphorus turns into phosphide. Nitrogen, nitride. Sulfur, sulfide. So now that we have our rules, let's apply our rules to try to name a few compounds. So Na2O. So first things first, I'm going to write the name of my metal. And Na corresponds to sodium. Okay, and now I write the name of my nonmetal. So my stem is ox for oxygen, and then I place at the end of my stem IDE. So this would be sodium oxide. What's really cool about this naming convention is that you don't have to specify the number of each ion. It is implied from the charge. Does this first example make sense to everyone? Does this first example make sense? So let's do another example. This time we have CaI2. So first we write the name of our metal, which is calcium. And then I, so we have iodine. So we use the stem iode, followed by the IDE ending. So this would be calcium iodide. Does this example make sense to everyone? Do these examples make sense? Any questions? So what we're now going to do is we're going to have you try and name the following compounds, and I'd like you as a bonus to specify the charge of each ion. So let's look at these first two examples, and let's try to name these two compounds, and we'll give everyone about 3 minutes to work on these examples. And we already see some proposed names in the chat. Let's try to get a reasonable pool of responses, and don't be shy to contribute your responses. As the more responses I see, the more I'm able to fine-tune my feedback to help address common misconceptions. We're seeing a reasonable pool of responses so far. Let's try to get a few more responses in the chat, and we'll discuss in about 1.5 to 2 minutes. And let's try to get a few more contributions in the chat, or if you have a question that I can address, You can also ask a question in the chat or verbally, and we'll discuss this example in about another 30 seconds to a minute. Okay, so first and foremost, for BAS, let's name our cation. Our cation is barium. S corresponds to sulfur. So we write the stem of sulf followed by the ending of IDE. So this would be barium sulfide. Okay. Next on our list, ALN, we write the name of our cation, which is aluminum. And then N for nitrogen, we use the prefix of nit. And then we change the ending to IDE. So this is aluminum nitride. Do these two examples make sense to everyone? Do these two examples make sense? Any questions? If we wanted to specify the charge, we know barium prefers a 2+ charge as it's a 2A element, and sulfur prefers a 2- charge as it's a 6A element. Aluminum prefers a 3+ charge as it's a 3A element. Nitrogen prefers a 3- charge as it's a 5A element. Just for completeness sake. Let's take a look now at the following set of examples. And now that we've had our first exposure to naming ionic compounds, let's do a series of 4 examples. Let's spend about 5 to 6 minutes on these 4 examples, and let's try to name each of these ionic compounds. And even if you're stuck on 1 or 2 of them, that's okay. What I want you to do is just let me know what you think. What do you think is the name for any of these proposed ionic compounds? And just take it one by one. However many you can answer, that's great while you're learning this material. And if you have questions, don't be shy to ask me in the chat or verbally, and I'd be happy to answer your questions. But the main thing is just to start taking the first steps to try to name these compounds and proposing your names for these compounds. So let's continue working on these examples and let's try to name each of these compounds. And we'll discuss the names for each of these compounds in about another 5 minutes. And we're already starting to see a few proposed responses in the chat. And don't be shy to chime in, even if your responses are different. That's okay. And we're starting to see a reasonable pool of responses in the chat, and we'll discuss this example in about another 3 to 4 minutes. It's really good to see students explaining the logic behind their responses. And even if you have a name for just one of these compounds, don't be shy to submit the name. There's no penalty, no risk to submitting. And the more responses I see, the more I can help provide feedback and answer any questions that you have. And you can even message your responses to me privately, and I'd be happy to take a look at them and provide feedback during these in-class problem-solving sessions. So really don't be shy, and we'll discuss this example in about another 2 to 3 minutes. And don't be shy to submit your proposed responses in the chat, or if you have a question, don't be shy to ask it in the chat or verbally. And we'll discuss this example in about another minute to a minute and a half. Okay, so let's discuss this example. So K2S, so we write the name of our cation, which is potassium. S, we write the stem of sulf for sulfur, and we change the ending to IDE. So this is potassium sulfide. Next, we have CaCl2. We write the name of our cation, which is calcium. Cl, we write the stem of chlor, and then we write the ending of IDE for our anion. In the next example, we have our good old friend barium as our cation, and then P corresponds to phosphorus, which has the stem of phos followed by an ending of IDE. So this would be barium phosphide. B2O3, we write the name of our cation, which is boron. And then for oxygen, we write our stem of ox, and then we add our ending of IDE. Does this make sense to everyone? Is everyone comfortable with this idea? Do these examples make sense to everyone so far? Any questions on these examples?
Professor,
Yes.
why calcium chloride, that chloride don't write as Cl2, but I look like a Ci2.
So if we're referring to iodine, it would be capitalized like this. And just as a follow-up, as we're talking about binary compounds, they will only have 2 different elements, never 3. Does that make sense?
Yes, thank you.
Perfect. Any other questions that I can address? Okay. So let's talk about writing the formula of a binary ionic compound from the name. Okay. So first and foremost, you're primarily going to deal with a main group metal or a fixed charge metal. Remember those, like silver plus, cadmium 2 plus, zinc 2 plus. Don't forget about them. And a non-metal. And this is where your formula rules are really going to come into play here. So first, we identify the metal cation from the name in the periodic table. You then identify the non-metal anion. This is the anion with the ending in IDE. And then using the periodic table, you're going to determine the charge of each ion. So for example, if we're looking at silver chloride, we know silver has a charge of +1 and chlorine has a charge of -1. Remember, because chlorine is a 7A element, 7 minus 8 is -1. Now that we have each of our charges, all we have to do is cross our charges into our subscripts. And that gives us our final formula for silver chloride, which would be AgCl. You can also do a check to verify the total charge of the ions match the total charge of the ionic compound. So we know our total charge of 0 is equal to the charge of our cation times the number of cation plus the charge of our anion, which would be -1 for chloride times the number of anion, and that in turn gives us a total charge of 0. So we've assigned our formula correctly. Does this process make sense to everyone? Does this process make sense? Okay, so let's do another example. Let's try to write the formula of the following compound. So potassium is K, as a 1A element, has a +1 charge. Selenide, that's selenium, and as a 6A element, we have a 2- charge. Writing out each of our charges, we then cross our charges into the subscript, and that gives us K2SE, or potassium selenide. Does this example make sense? Is everyone comfortable with this method? Okay. So let's now take a moment and let's work on these first two examples. And I'd like you to write the formula for the following compounds. And remember, your formula should be the simplest whole number ratio of atoms. So let's work on these examples for about 2 to 3 minutes, and then we'll discuss. And we already have our first some proposals in the chat. Let's just make sure that we're double checking the charges for each of our ions. And we'll discuss this example in about another 1.5 to 2 minutes. And don't be shy to contribute your response or a question to this class discussion, and I'd be happy to provide feedback. And remember, in your proposed formulas, you want to make sure that you have your charges correctly assigned for each of your, yes, sorry, that's, I see the, yeah, the spelling for cesium. The Word document doesn't like the name for cesium and it keeps correcting it automatically. But yes, this would be the name for cesium when you're trying to match the periodic table. Let's try to get a few more proposed formulas in the chat, and we'll discuss in about another 30 seconds to a minute. Okay, so looking at lithium sulfide, we have lithium, which is a 1A element, which we expect to have a charge of +1. Sulfide is sulfur, which is a 6A element, which has a 2- charge. We write out the charge of each of our ions, and then we cross the charges, and that gives us lithium sulfide, Li2S. Make sure you have your charges correctly noted for each ion in order to write the formula. Does that make sense? Let's look at the cesium oxide example. So cesium is a 1A element with a +1 charge. Oxide is indicating oxygen, which is a 6A element with a 2- charge. So we have cesium plus O2-. We cross our charges. That gives us CS2O. Do these examples make sense? Perfect. So now that we've seen some examples and we've given ourselves time to revise, let's try to write the formula for the following 2 compounds. And let's work on this next set of examples for about 3 minutes. So I'd like to see some proposed formulas in the chat, or at the bare minimum, just some questions if you're unsure how to handle these problems. Or if there's some part of this problem-solving method you would like me to clarify further. So let's work on these examples for about 2 to 3 minutes, and then we'll discuss. And we're starting to see some proposed responses in the chat. Let's keep working on this example and we'll discuss in about another minute and a half. And it's nice to see that we have a pool of students submitting their responses. Let's keep working and we'll discuss in about another minute. And if you have any questions working on these examples, don't be shy to message me in the chat or to ask your questions verbally. It's good to see this level of participation in the chat, as it's really helpful for giving me a sense of how the class is working through the material. Okay, so aluminum oxide. So aluminum is a 3A element, so it should have a 3+ charge. Oxide, oxygen, 6A element with a 2- charge. We take each of our ions and we cross our charges, and that gives us Al2O3. Does this make sense to everyone? Is everyone comfortable with this idea? Let's look at barium chloride now. Barium is a 2A element with a 2+ charge. Chloride is a 7A element with a -1 charge. We write out the charge of each of our ions and then cross our charges, and that gives us BaCl2 for barium chloride. Does that make sense to everyone? Does this example make sense to everyone? Any questions before we move on to another topic?
I have a question for the CL.
Yes.
Why wasn't the 7A incorporated?
It is because for the 7A, for anions, remember our charge is equal to our group number -8, which is 7 - 8, which gives us a charge of -1. Does that make sense?
Oh, okay, yes.
Perfect. Any other questions I can address? Okay, so let's keep going now. And let's talk about polyatomic ions. Now, again, I'm showing you this polyatomic ion table. You're going to need to memorize the following polyatomic ions. You're going to need to be familiar with their names, formulas, and charges. And we discussed shortcuts for memorizing polyatomic ion names earlier in this chapter. So with that initial request out of the way, you're welcome to use this table for these in-class problem-solving activities, but you're going to want to start to, as you solve these problems, use the table less and less, and more try to recall from memory. Okay, So for naming polyatomic ionic compounds, it's really straightforward if you know your polyatomic ion names. First, you write the name of your cation, which can either be a metal or a polyatomic ion. Then you write the name of your non-metal anion. And there's one little catch. If the non-metal anion or cation is a polyatomic ion, you write the name of the polyatomic ion with no changes. You just write the name as is. So let's look at an example. So CaCN2. So we write the name of our cation, which is calcium, and then Cn minus. What do we call that? What do we call Cn minus? What do we call that polyatomic ion?
Cyanide?
Yep, cyanide. And we just write the name exactly as is, no changes. So this would be the name for this compound. Looking at this next example, KNO3, writing the name of our cation, we have potassium. And then for NO3 minus, what do we call NO3 minus? What do we? Nitrate, exactly. So this would be potassium nitrate. Exactly right. Notice how the ending of our polyatomic ion is unchanged. Does that make sense to everyone? Does this make sense to everyone so far? So it's not too bad if you happen to know the name and formula of your polyatomic ions. Any questions before we work on some examples in small groups? So what I'd like you to do now is I'd like you to try and name the following compounds, and we'll spend about 3 minutes on this next example. And don't be shy to share your proposed name for these compounds in the chat or verbally. And we're already starting to see some proposed names in the chat. Let's try to get a few more responses and we'll discuss in about 1.5 minutes. And we're starting to see a reasonable pool of responses in the chat. Okay, so let's discuss these examples. So NH4, we call this ammonium, and SO4 2 minus is known as sulfate. So the full name would be ammonium sulfate for this compound. Does that make sense to everyone? Is everyone comfortable with this so far?
I'm not understanding this one.
So in order to name compounds containing polyatomic ions, you identify the polyatomic ions in the formula, and then using the table, you write the name of each polyatomic ion individually. So NH4 plus is ammonium, SO4 2 minus is sulfate. Does that clarify? Does that make sense?
Yes.
Perfect. So looking at this next example, we name our cation and polyatomic anion. So calcium, so Ca is calcium, and phosphate, which is, PO4 3 minus is known as phosphate. So the full name for this compound would be calcium phosphate. Does that make sense to everyone?
Professor, quick question. On the NH, on the polyatomic ions, is that one on there? Because I don't see it.
Ah, yes, it is. Ammonium is right here. It's a cation, so it's under the cation.
Oh, on the top.
Yep.
Okay. All
Does
right.
that make sense?
Yes, thank you. Sorry.
No problem at all. So, any other questions before we move on now? Okay, so now we're just going to look at a small variant of polyatomic ion containing compounds. These are known as hydrogen containing polyatomic ionic compounds. So some polyatomic ions contain hydrogen atoms bonded to a base polyatomic ion. It's funny because many of these polyatomic ions also function as bases. So it's a doubly useful definition. Okay, so for example, if you start with carbonate and you add a hydrogen, it becomes hydrogen carbonate. You start with phosphate, you add 2 hydrogens, it's dihydrogen phosphate. So adding a hydrogen atom, H plus, reduces the charge of the polyatomic ion by 1 per hydrogen atom. Does everyone see how the charge goes down when we add hydrogen ions? Does everyone see how the charge decreases? It becomes a smaller number when we add hydrogen ions. Does that make sense to everyone?
Yes, so would we always just subtract the one?
Yep,
Charge?
exactly.
Okay. Dealing with hydrogen.
Yep, you subtract 1 per hydrogen.
Got it, thank you.
So like phosphate, we have PO4 3 minus. If we're adding 2H plus, 3 minus 2, well, negative 3 plus 2 gives us negative 1. That's why H2PO4 has a negative 1 charge. You're just adding the charges together of all of your components. Does that make sense?
Yes, sir.
Perfect. So how do we name hydrogen-containing polyatomic ions? So first you write the name of the polyatomic ion base. So let's look at naming HSO4. HSO4 minus. So first, where did we get that? Well, we have H plus and SO4 2 minus. And that in turn gives us HSO4 minus, just adding up our charges. So we write the name of our polyatomic ion base, which would be SO4 2 minus, which is known as sulfate. Okay, so that's the base. Next, we place hydrogen in front of the name of the polyatomic ion. So in this case, if we're looking at HSO4 minus, we write the name hydrogen. So this would be hydrogen sulfate. Does that make sense? Yes, the rule for adding hydrogen applies to any polyatomic ion where your hydrogen containing polyatomic ion has a net charge. Now, there's one little catch that you have to remember. If there are 2 or more hydrogen atoms, make sure you add the appropriate prefix in front of the hydrogen term. So for example, H2PO3 minus would be known as we have 2 hydrogens, we use the prefix of di. So this would be dihydrogen. And then we write the name of our base polyatomic ion, which in this case is phosphite. Does that make sense to everyone?
Professor, in the chart you gave us for the HSO4, and instead of hydrogen sulfate, it says bisulfate.
Yes, that's an informal name. You can use the informal name, but the process for writing the name for hydrogen containing polyatomic ions that I'm showing you here is general and applies to all hydrogen containing polyatomic ions.
Okay, so don't worry about saying bisulfate, just learn
Yeah,
the hydrogen.
that would be a valid name, but it's not quite following IUPAC. It's more of an informal name.
Got it, thank you.
Perfect. Now, there's one little warning that I need to provide for this section. If a polyatomic ion contains hydrogen and it is neutral, it is an acid, and acids have different naming conventions. So for example, H2SO4 is not an ion, right? We don't see a net charge, right? This is an acid. So this would be named as sulfuric acid. Does everyone notice the dramatic shift in naming when we go from a hydrogen-containing polyatomic ion to an acid which has no charge, no net charge? Does this make sense to everyone? Okay, so let's do some examples. Let's do some examples. So I'll do the first in this set and you'll do the next. So first and foremost, let's look at this formula. So I'm going to write the name of my cation, which is lithium. And then HCO3, I'd write it as hydrogen carbonate. We'll talk about naming rules for acids later on in this chapter, so don't worry about that. We'll get to that momentarily. Let's focus on these hydrogen-containing polyatomic ions for now. So we've done this first example where we've named lithium hydrogen carbonate. I'd like you to take a moment and work on naming the following 2 compounds that contain hydrogen containing polyatomic ions, and we'll discuss this example in about 3 minutes. So let's try to name these compounds. And if you have a question naming any of these compounds, don't be shy to ask it verbally or in the chat.
So Professor, for the second one, the calcium hydrogen, since doesn't have any charge, so that's an acid. We need to name it as an acid.
You have to look at each of the ions individually. So in lithium hydrogen carbonate, when you cross the charges, you have lithium plus and HCO3 minus. So the polyatomic ion itself has a charge, but the ionic compound is neutral. You're focusing on the polyatomic ion, and make sure your polyatomic ion has a net charge. And in this case, it does. HS has a charge of -1. Does that make sense?
Yes, it does.
Perfect. So we're already starting to see some proposed names for these two compounds in the chat. Let's keep working on these examples and we'll discuss in about another minute and a half. And it's good to see this level of participation throughout this class session. And it's good to see that if students have questions, they're asking it in the chat or verbally. This dialogue is really helpful in these problem-solving sessions.
Professor, if there are two of, let's say, hydrogen, we say bihydrogen or dihydrogen?
It would be dihydrogen.
Oh, di, okay.
Mhm.
So what is bi? Bi is just that an off name?
So it's not a commonly used prefix.
Okay.
It can be used informally to describe polyatomic ions with one hydrogen attached, though that nomenclature is not as common.
Okay, got it. Thank you.
Okay, so let's focus on naming these compounds. So first and foremost, we have calcium as our metal, and then HS would be named as hydrogen, as we have one hydrogen, and then sulfide, because S2 minus is known as sulfide. Does this first example make sense? Is this
Yeah.
first? Perfect.
So the hydrogen sulfide, so that 2 that's outside, it doesn't mean anything. I thought that was 2 hydrogen.
It just tells you the number of that polyatomic ion. So what it's telling us is we have 2 of these HS units. But we're only concerned in a single polyatomic ion, how many hydrogens do we have?
Oh, okay, gotcha.
Does that make sense?
Yes. So we wouldn't use the dihydrogen part.
Not in this case.
Okay.
We will in this next example, however, as we write the name of our cation, which is sodium. We have 2 hydrogens, so in this case we do dihydrogen. And then our base polyatomic ion is phosphite. So this would be sodium dihydrogen phosphite, because our polyatomic ion has 2 hydrogens. Does this make sense?
Professor, the
Yes.
sheet you give to us said the HS is called bisulfite. Why this time you call hydrogen sulfide?
Those 2 names are both acceptable for the HS minus polyatomic ion. Bisulfite and bicarbonate are informal names, while the naming method that I'm showing you here are IUPAC naming methods.
Okay, thank you.
Yeah, so there are 2 different methods for naming the same compound. The IUPAC method is more general, and that's why it's preferred. Does that make sense?
Yes, thank you.
Perfect. So let's focus, now that we've had an example to attempt these problems, let's focus on naming these next 3 set of compounds. Let's work on this for about 3 to 4 minutes, and then we'll discuss.
Professor, when we are writing each component, we need to capitalize like calcium, hydrogen, and sulfide each separately, or just the
You can choose to capitalize the first letter of the first portion of the name.
Okay.
Yeah.
So big C, big H, big S on the first, right?
Yes, or you can just capitalize the C in calcium to start out with, and then everything else could be lowercase.
Lowercase. Okay, got it. Thank you.
Mhm. And then remember the prefix, if you have a hydrogen containing polyatomic ion, is hydrogen. Rather than hydro, it would be hydrogen. Otherwise, we're starting to see a reasonable pool of responses in the chat. Make sure that your names for the polyatomic ions are correct. And in fact, we've already seen some students correcting their names after they've double checked. So let's keep working on this example, and we'll discuss in about 2.5 to 3 minutes. And if you have any questions working through these examples, don't be shy to ask them verbally or in the chat.
Professor, and the last one, and the silver hydrogen chromate,
Yep,
we are adding only 1 hydrogen. Why chromate doesn't have a negative charge? 1 negative charge.
it does. but the silver has a +1 charge. So together in the ionic compound, the net ionic compound is neutral.
Oh, okay. I forgot about this silver. Thank you.
No problem at all. And we'll discuss these examples in about another minute to a minute and a half. And it's great to see a pool of responses proposed in the chat. Okay, so let's discuss. So first we break down our compound into our two ions. We write the name of our cation, which is calcium. And then we write the name of our polyatomic ion, which in this case would be hydrogen sulfite. Does this first example make sense to everyone? Hydrogen, because we have a hydrogen, SO3 2- is known as sulfite. Does this make sense to everyone?
Is that hydrogen is HYDROGEN?
Yes. Let me rewrite this just to make it a little bit easier.
Just making sure. I know you were saying.
Yep, it's hydrogen rather than hydro. Does that make sense?
Yes, thank you.
Perfect. Looking at this next example, we have magnesium 2+ and HP 2-. So this would be magnesium, hydrogen, and then P3- is known as phosphide. So this would be hydrogen phosphide. Does that make sense to everyone?
Why P is 2- and 3-?
Because remember when we add a hydrogen, the total charge decreases by 1.
Got you. Thank you.
Any other questions I can address on these first two examples? Okay, looking at the next example, we have silver plus and HCrO4-. So writing the name of our cation, we have silver, and then for HCrO4-, we'd write the name as hydrogen chromate, because CrO4 2- is known as chromate. Does this example make sense to everyone? Any questions on this example?
So in order to write the correct name, we need to figure out each atom's charge.
Yes, that is helpful because it allows you to identify the base polyatomic ion or ion, and that in turn allows you to name the polyatomic ion or anion correctly. Yes.
Thank you.
Any other questions that I can address? Okay, so let's now talk about a subclass of compounds that requires you to be a little bit careful, and this is where our charge rules really start to become quite useful. So we're talking about naming binary ionic compounds with variable charge transition metals. So transition metals can adopt a range of positive charges. So we can have iron 2+, iron 3+, iron plus. Now, Most transition metals adopt a 2+ charge, but the charge of a transition metal must be explicitly noted to avoid ambiguity. If I said iron chloride, I could be referring to anything from FeCl to FeCl2 to FeCl3. So this ambiguity is resolved by clearly specifying the charge of our transition metal. So if I said iron to chloride, I would be referring to only one of these formulas. Okay, so how do we name binary ionic compounds containing variable charge transition metals? So let's look at an example of COBr2. Okay, so first we write the name of our transition metal cation. So in this case, that's cobalt. Next, we write a Roman numeral indicating, and this is where the charge rules are important. You write a Roman numeral after the name of the transition metal cation, and this Roman numeral is telling you the charge of your transition metal cation. So in this case, if we reverse cross our charges, we get cobalt 2+ and Br minus. So we'd write in our name cobalt Roman numeral 2 to signify we have a 2+ charge. Does that make sense to everyone? Does that make sense to everyone so far? Now, if the anion is an atomic ion, you write the name and then you change the ending to IDE. So for example, in this case, we have cobalt 2 and then bromine would be written as bromide. So this would be the full name for COBr2. Now, just as a refresher, if the non-metal anion or cation is a polyatomic ion, you write the name with no changes. So for example, if we have NiNO32, we get nickel 2+ and NO3- for our charges. And so we'd write the name as nickel 2 and then NO3 2-. We just write the name of our polyatomic ion as is, so that would be nitrate. Does this make sense to everyone? Is everyone comfortable with these naming methods for variable charge transition metal containing compounds? Any questions?
Just real quick, just to reiterate, polyatomic meaning?
Polyatomic is an ion containing 2 or more atoms covalently bonded together.
Oh,
So
okay, yeah.
nitrate NO3-,
Thank
we
you.
have multiple atoms bonded together, and the molecule or this ion itself has a net charge. Does
Got
that
it.
make
Thank
sense?
you. Yes, sir.
Perfect. So there's one little exception that you need to remember. Fixed charge transition metals, silver, cadmium, and zinc form silver plus, cadmium 2+, and zinc 2+. You do not need to specify the charge for a fixed charge transition metal. So that's just one little trick in these problems. So let's do an example. I'll do the first, you'll do the next two. So FeSO3. So I reverse cross my charges. That gives me Fe plus and SO3 minus. Now I know sulfite has a charge of 2-. So what I'm going to do is I'm going to multiply each of my charges by 2. That gives me Fe2 plus, SO3 2-. And now I can name this compound. So we write the name of our cation, iron. You put the charge as a Roman numeral in parentheses, and then we write the name of our anion, which is sulfite. SO3 2- is known as sulfite. So this compound will be known as iron 2 sulfite. Any questions on this first example? Any questions on this first example?
So Professor, why did you times 2 on each one? Are we allowed to do that ourselves?
Yes, yes. And the reason why I multiplied each of our initial charges by 2 is I know sulfite from my table has a 2- charge. So then I need to adjust both my cation and anion charge such that sulfite has the correct charge. Does that make sense?
So if we see something like known compound doesn't have the right charge, we just multiply it until we make it correct, right? That's what we're
Yes,
doing?
but you have to multiply both of the charges by the same number. So that way the ratio stays the same.
Okay, got it.
Perfect. So let's work on these next 2 examples. Let's spend about 2 to 3 minutes on these next 2 examples. Let's focus on naming these 2 compounds, and then we'll discuss momentarily. And remember the trick associated with fixed charge transition metals. For some of the responses I see in the chat, the logic would be correct for most transition metal containing compounds, but for fixed charge transition metal containing compounds, you do not have to specify the charge. So zinc is one of the exceptions, along with silver and cadmium.
So we just say zinc iodide, right? Not
Yep, exactly right. Let's try to get a few more responses in the chat. And if you have any questions, don't be shy to ask them in the chat or verbally. And we'll discuss in about another 1.5 to 2 minutes. And let's try to get a few more responses in the chat, and we'll discuss in about another 1 to 1.5 minutes. Okay, so let's discuss. So first, we write the name of our cation, which is zinc. And then we write the name of our anion, which is iodine, which changes to iodide. Remember, zinc is a fixed charge transition metal, so we don't need the charge in parentheses. For this next example, if we reverse cross our charges, we end up with cobalt 2 plus and HC2O4 minus. This is a derivative of oxalate. So now that we have all of our charges established, we write the name of our cation, which is cobalt. We write the charge in Roman numerals, and then we write the name. And since this is a hydrogen-containing polyatomic ion, we'd write the name as hydrogen oxalate. And there we have the complete name for this compound. Does that make sense to everyone? Any questions on this example? Any questions on these examples? Okay, so
Wait, Professor, I just want to clarify really quick. Okay, so
Yes.
if it's a polyatomic ion and there's a hydrogen, it's just going to be hydrogen and then the ion. But if it's just
Yep.
like an atom, then it's hydro.
if it's just it's hydrogen in all cases if it's a hydrogen containing ion.
Okay. Oh, when is it hydro?
Never.
Oh,
The
okay,
only
never mind.
hydro is a prefix that is reserved when talking about acids, which are
Oh,
an
okay.
entirely different class.
Okay.
Does that make sense?
Yes, thank you.
Perfect. So let's try to name the following 3 compounds, and let's work on naming these 3 compounds over the next 3 to 4 minutes. And if you have any questions on these examples, don't be shy to ask it in the chat or verbally, and I'd be happy to address your questions. I'd like to see a reasonable pool of responses for our discussion, so don't be shy to contribute your proposed names for these compounds in the chat.
Professor, what charge lead usually takes?
Lead can adopt a range of charges.
Okay.
So you'd have to calculate the charge of lead using the charge of your component ions in the compound.
Got it. Thank you.
Perfect. And let's try to get some proposed names for each of these compounds in the chat. And we're starting to see some proposed responses in the chat. Let's keep working through these examples and we'll discuss in about 3 minutes. And we're starting to see a reasonable pool of responses in the chat. And we will discuss in about another minute and a half to 2 minutes. And remember, the charge should be specified as a Roman numeral. And we'll discuss in about another minute. We have a nice pool of responses in the chat, so it's good to see students participating and sharing their proposals in the chat. And we'll discuss these examples momentarily. So first and foremost, AgClO4. So we have silver plus and ClO4 minus. Silver is a fixed charge transition metal, so we don't need to include the Roman numeral. So we have silver, and then ClO4 is known as perchlorate. One moment. Oops, sorry about that. There's just a small amount of lag in OneNote. There we go. So this would be silver perchlorate. Does this first example make sense to everyone? Does this first example make sense? Let's look at this next case. So if we reverse cross the charges, we'd preliminarily get lead 2 plus and Cr2O7 minus. Now, this may not seem like an issue at first glance, but remember that Cr2O7, which is known as dichromate, is known to have a charge of 2 minus. So then we need to multiply both of our charges by 2. That gives us lead plus 4 and Cr2O7 2 minus. So then, now that we have our corrected charges, we write the name. So we have lead 4, and then we write the name of our polyatomic ion, which is dichromate. Does this next example make sense to everyone? Does this example make sense to everyone?
Yes, I have a quick question. So I did it a different way, and then correct me if I'm wrong, please, just in case. So I did get lead for dichromate. However, I did for PB for lead. I just did. I just used for
Use the
because
group number?
yeah, the group number. Is that
So,
incorrect?
because lead is a transition metal, it can adopt a charge that's not just +4. Lead can actually adopt a +2 charge as well, in an example like so.
Okay.
So the group number wouldn't work for lead because it's a transition metal. It can adopt a range of possible charges.
Okay. Can you explain? So you said that you multiplied the lead 2 plus times 2, and then the chromium oxygen times 2. So how did you get 2 negative? I guess I'm kind of confused with that.
Because we know dichromate in our table is supposed to have a 2 minus charge. We need to take our charge of -1 and multiply it by 2 to convert it to the correct charge of 2 minus.
Oh, okay, gotcha. Okay, thank you.
Multiply both of our charges by 2 in order to maintain and maintain balanced charges and a neutral ionic compound.
Okay, so it is okay for us to then multiply what is needed in order to get to where we need to be at,
Yes.
if that makes sense. That's
As
kind
long
of
as
difficult.
you're multiplying the charge of your cation and anion by the same number.
Got it. Thank you.
Perfect. Finally, we have CrHCO3. So we reverse cross our charges. We get chromium 3 plus and HCO3 minus. Everything looks good from a charge perspective. So we write the name of our cation, which is chromium. We put the charge as a Roman numeral, and then we write the name. In this case, this is hydrogen carbonate. So this is chromium 3 hydrogen carbonate. You can also call it chromium 3 bicarbonate if you're so inclined. Does this make sense to everyone? Okay, so that's all I have planned for today's lecture session. So